Hello and welcome to the AI Research Roundup. I am Alex. Today is May 8th, 2025. We are looking at a research paper from Hugging Face's trending list, published 3 days ago, titled FormalMATH, Benchmarking Formal Mathematical Reasoning of Large Language Models. This paper introduces FormalMATH, a new large-scale benchmark. It is designed to test how well large language models, which are advanced AI systems, can perform formal mathematical reasoning. This means proving mathematical statements with strict logical steps. This research also presents a novel human-AI pipeline to create these formal problems efficiently. So to build this extensive formal math benchmark, the researchers developed a clever system. And Figure 1 here gives us a visual walkthrough of this human-in-the-loop pipeline. It starts with an auto-formalization query, a math problem in plain English. Then auto-formalizers. These are specialized large language models. Attempt to translate this into Lean 4. Lean 4 is a formal proof assistant. Think of it as a special programming language and software tool used to write and check mathematical proofs with absolute logical rigor. After several automated filtering steps, including syntax checking, semantic checking, using other large language models, and even negation filtering with AI provers, the final step is human verification by math experts. This efficient pipeline was key to creating such a large number of formal problems. Alright, building on that pipeline, these next charts are quite revealing. First, we see how current AI theorem provers, AIs that automatically prove math theorems, fare on this new formal math benchmark. The performance is, well, quite low. Even the top models, whether they use a search strategy like best first tree search or a direct attempt via single pass generation, only hit about a 16.5% success rate. This is measured by pass at k, essentially the chance of a correct proof in k tries. Then, a funnel chart revisits the pipeline's efficiency, showing about 22% of initial problems make it into formal math, underscoring its rigorous selection. Okay, so to really appreciate the challenge that formal math presents, and why those low success rates we just talked about are so telling, Table 1 here gives us a great comparison. It lists existing Lean 4 benchmarks. These are standardized test sets for AI systems that work with the Lean 4 proof assistant, alongside formal math. You can immediately see the difference in scale. Formal math has 5,560 problems, vastly more than others like MiniF, 2F, or ProofNet. Plus, it covers both Olympiad and undergraduate, or UG, level difficulty, making it much more comprehensive. This scale and breadth really underscore its importance. Now, Figure 3 gives us a closer look at that breadth we were just discussing. It presents two pie charts showing the distribution of mathematical domains within the formal math benchmark. The left chart details the undergraduate level problems. Here, we see a good mix with integral problems making up about 30.8%, followed by pre-calculus at 18.9%, and algebra at 15.9%. The right chart shows the high school level problems, where algebra is dominant at over 50%, and number theory is also substantial at 22.3%. This visual breakdown really emphasizes the diverse mathematical areas formal math covers. So following on from that diversity of topics within formal math, this radar chart really drives home how current AI theorem provers handle these different mathematical areas. You can see various domains like algebra, pre-calculus, and integral radiating out from the center. The lines plotted on the chart, which represent model performance, stretch further out towards algebra, indicating better success there. However, these lines are much closer to the center for areas like multivariable calculus and differentiation, showing a real struggle. This pattern clearly highlights a significant domain bias. The artificial intelligence systems are not equally capable across all mathematical subjects, which is a major hurdle. Alright, moving from the types of math problems, these next two graphs explore how AI models attempt solutions. They plot pass at k accuracy, the chance of a correct proof, against sample budget, basically the computational effort. We see models trained with supervised fine-tuning, or SFT, that is, learning from examples, and reinforcement learning, or RL, which means learning via trial and error. Both charts compare vanilla reasoning, naive chain of thought, where the AI thinks step by step, and natural language augmented chain of thought. Interestingly, adding natural language hints to the chain of thought actually reduces success. The yellow line, representing this natural language augmented approach, is below the blue line for naive chain of thought, suggesting informal explanations can hinder formal logic. So that insight about natural language sometimes hindering formal proofs really sets the stage. The authors introduced FormalMATH, a benchmark with over 5,500 formally verified problems precisely defined for computers, to truly test AI in formal mathematics. This was created using auto-formalization, an AI-assisted method to translate math into computer-verifiable language. The key takeaway is clear. Current AI provers still face major hurdles, with low success rates, around 16.5%, and significant biases across different math domains. Formal math really underscores the journey ahead. That is all for this AI Research Roundup. Thanks for tuning in.